So here's the question we have. 2 players, 3 strategies for each. The question is find pure and mixed strategy, all pure and mixed strategy Nash equilibrium of this game. Well, let's first find the pure strategies, because if you find the pure strategies, it's going to give you an idea what other pure strategies may be strictly dominated. So here, if you look at it, if the player 1 plays U, the best response is R, because 5 is the highest. If player 1 plays C, best response is M. If he plays D, the best response is R. So the same thing if player 2 plays left, or if player 1 believes that player 2 is going to play left. You can interpret it this way. The player 1's best response then would be U. If he plays, if player 1 believes that 2 is going to play M, the best response for 1 is C. And then finally, if 2 plays R, the best response for player 1 is U, because 6 is higher than 2 and 3. So that's it. You just circle, if you want to, the payoffs where all numbers kind of underlined, because that represents that each player is best responding his opponent. But at the end, do not write 6, 6, 6, 5 are the Nash equilibrium. Okay, I'm obsessed with correct language. These are outcomes, okay? They can't be Nash equilibrium. You have to write the strategy profiles. So here, CM is one pure strategy Nash equilibrium, and then the other one is UR. That's it. These are the pure Nash. Okay. Well, what about the mixed Nash? If you want to find a mixed Nash of this game, it's a 3x3, nearly impossible. All right? So you have to simplify it. I mean, get rid of some strategies, as many strategies as you can. Well, here, a very simple inspection would say, you have some sort of feedback when you get the Nash equilibrium strategies. What is this feedback? Well, look, player 1, C and U, all right? U and C, these are, I'm going to put them in a bracket because it's not a profile. So these are strategies that are part of Nash equilibrium, all right? Some Nash equilibria. And for player 2, M and R, these are part of strategies that are part of some Nash equilibrium. So that means those strategies are never strictly dominated, all right? If they were strictly dominated, they couldn't be part of Nash equilibrium. So when you're looking for, so I'm going to apply iterated elimination of strictly dominated strategies to simplify this game. So for this reason, look for strategies that were not best response to a pure strategy, okay? So they are probably a good, the best candidates, not the best. They are the candidates to be strictly dominated. They may not be strictly dominated though. It's not a guarantee. Okay, so here I'm going to look at D for player 1 and L for player 2. So let's look at L. So 3 is worse than 4. I'm comparing with M. If it doesn't work, I'm going to compare with R. So 3 is worse than 4, 3 is worse than 6, 2 is worse than 5. You know what? Whatever player 1 does, L is worse than M. So M strictly dominates L, or L is strictly dominated. All right? So player 2, will never play L. So you can get rid of it. Fine. Let's in fact be, neat. And so let me rewrite everything. There you go. So now, again, for player 2, there's no more elimination. How do I know that? Again, M and R are part of Nash equilibrium strategy profiles, so they can never be eliminated. Well, what about D? D is never a part of a Nash equilibrium, so it may be dominated, all right? It may not be. D strategy is not strictly dominated by any mixture of U and C, all right? Well, how do you see that? Simple, just call a mixed strategy by R1 minus R, okay? I mean, you'll see why I'm using notation R later, because I'm going to use P and Q afterwards. So let's say player 1 mixes U and C with probability R and 1 minus R. Is there any R in between 0, 1, obviously, so that this mixture, the expected payoff of this mixed strategy is better than the expected payoff or the payoff of strategy D, whatever player 2 does? Well, expected payoff of player 1, obviously, when he plays R, is this. Well, obviously, it depends on what second player does, right? So here, when player 2 plays M, what is the expected payoff of this mixed strategy? Well, player 1 is going to get 2 with probability R and 6 with probability 1 minus R. So it's 2R plus 6, 1 minus R. Okay? Well, what is the the expected payoff of this mixed strategy if the second guy plays R? In this case, it's 6 times R plus 2 times 1 minus R. Right? Well, what is the expected payoff of playing D? Well, there's no expectation here, right? Because the D is a pure strategy. So if the second guy plays M, he's going to get 5. If he plays R, he's going to get 3. So all I have to do is to compare these two numbers and then also compare these two numbers and see whether there exists an R so that 2R plus 6, 1 minus R is greater than 5, and also 6R plus 2, 1 minus R is greater than 3, strictly. Because that's the definition of strict elimination, right? So it has to be strictly higher, not equal. Well, if you do this, if you do the algebra, I mean, let me do it. So this is 6 minus 4R greater than 5, which is equivalent to saying 4R is less than 1. So R is less than 1 over 4. So if R is less than 1 over 4, when player 2 is playing M, this mixed strategy is going to be better than D. Okay, but what about here? This should also hold. All right, well, that implies what? This is 2 minus 4R greater plus 4R greater than 3. So 4R greater than 1, so R greater than 1 over 4. So okay, here I have some sort of contradicting two facts. What are these facts? So this fact says, if this is the case, well then the mixed strategy will dominate, quote unquote, this strategy D only if player 2 is playing M. If this holds, well then mixed strategy will dominate D only if second player plays R. But the definition of strict domination means whatever player 2 plays, the mixed strategy should be dominating D. Well, there's no such R. All right? I mean, R cannot be less than 1 over 4 and at the same time more than 1 over 4. I mean, it's impossible. All right? And when R is equal to 1 over 4, don't forget, these are not inequalities, they're equalities, and in which case it's not strict domination. So, that's basically the conclusion. There is no mixed strategy of U and C which strictly dominates D. Conclusion, D is not strictly dominated here. So I cannot eliminate it. All right? Okay, so what does that mean? That means I have to deal with this 3 by 2 matrix then. All right? So this is what I'm going to do. Let's start with the player who has less strategies. And here it's player 2. So player 2 has only 2 pure strategies. Let's give them some mixture, P1 minus P. Right? Eventually, I'm trying to find a mixed strategy profile. So player 2 may be playing a mixed strategy according to those probabilities, let's suppose, and see what I can deduce. Well, given the second player's probabilities then, I can calculate expected payoff of player 1 when he plays each pure strategy, right? There are 3 pure strategies he can play. The first one is U. So I'm going to denote it this way. So expected payoff of player 1 when he plays U and his opponent randomizes according to probability P. And then his expected payoff if he plays C instead. And then, I don't know why I put 2 there. It's 1. And then expected payoff of playing D when his opponent mixtures with probability P. So here, what are the payoffs? Expected payoffs. So player 1, when he plays U, he's going to get 2 or 6 with those probabilities. So it's 2 times P plus 6 times 1 minus P. It is 6 minus 4P. Okay. What about this? Expected payoff of playing C. It's 6P plus 2, 1 minus P. So it's going to be 2 plus 4P. And here, expected payoff is going to be 5P plus 3, 1 minus P. So it's going to be 3 plus 2P. I want to show you how we find all mixed strategy Nash equilibrium. So what I'm going to do here is sort of answer a simple or simpler question. Can there be any Nash equilibrium, mixed strategy Nash equilibrium, where player 1 plays D with a positive probability? All right, so this is the question I'm asking. Is there any mixed Nash equilibrium where player 1 plays D with a positive probability? Is it possible? I mean, if it is not possible, well, then actually, yes, I can just ignore, get rid of D and work on this 2x2 simpler game. All right? So let's answer this question. So I'm attacking the big question sort of one small piece at a time. Well, what does that mean, having a Nash equilibrium where D is played with a positive probability? It means player 1 is going to, D is going to be best response for player 1, right? So best response means what? The expected payoff of player 1 when he plays D, remember his opponent is randomizing with respect to P, probability P, which we don't know what it is yet. But this thing should be greater than or equal to his expected utility or payoff if he plays C, and his expected payoff of playing D is greater than or equal to his expected payoff if he plays U. So if these two inequalities hold, that means D is a best response for player 1. And so he's going to play D with a positive probability. I mean, maybe with probability 1 if both of them are strict. But it is going to be positive probability. If it is equal, well, then he may play a mixed strategy, but still D is part of it. Okay, so if you want to answer this question, you have to see what these two equations are going to give you. So let's do that. What is the expected payoff of playing D? Well, it is 3 plus 2P greater than or equal to expected payoff of playing C is 2 plus 4P. So if you simplify that, 2P is less than or equal to 1. So that basically means P is less than or equal to 1/2. All right, so if the second guy randomizes with a probability P less than or equal to 1/2, player 1's best response, not best response yet because I did not look at the second part, but D is going to be giving a better, higher, weakly higher payoff than C. All right, let's look at this one. Again, expected payoff of playing D is 3 plus 2P greater than or equal to expected payoff of playing U, 6 minus 4P, which basically says 6P is greater than or equal to 3, so therefore P is greater than or equal to 1/2. And because this is an AND statement, if both of those hold, which can hold only if P is equal to 1/2, so if P is equal to 1/2, D is a best response for player 1. Otherwise, it's never a best response. All right? Meaning, there is no p-value other than 1/2. So if p is not equal to 1/2, d is not a best response. Therefore, it cannot be part of Nash equilibrium. Can't be part of Nash equilibrium. I mean, d can't be part of Nash equilibrium. So what does that mean? That means there can be a mixed strategy Nash equilibrium where player 2 plays M and R with equal probabilities, and D is a best response. But the thing is, there might be a bunch of other mixed strategy Nash equilibrium where P is not 1/2, but in this case, D is not played. D is not a part of Nash equilibrium because it's not a best response. So, okay, let's go with this one first. What if P is equal to 1/2? Note one thing. When P is equal to 1/2, what happens to those expected payoffs? They're going to be equal, right? All of them will be equal. I mean, expected payoff of playing D is equal to expected payoff of playing C, and expected payoff of D is equal to expected payoff of U. So U, C, and D, they all are going to give player 1 the same expected payoff. Again, if P is equal to 1/2. So that means what? Player 1 is going to be indifferent between U, C, and D. So if there is a mixed strategy Nash equilibrium where P is equal to 1/2, well then U and C and D, all three can be a part of this Nash equilibrium. All right? So that's conclusion 1. Conclusion 2, if P is not 1/2, well then D is not part of Nash equilibrium. So I only need to check this 2x2 game. So there are 2 cases I generated, and I need to look at those 2 cases separately. Clear? All right. So let's look at the first case where P is equal to 1/2 and player 1 is indifferent between all 3 actions. So what should I do next? Well, this time I mean it's time to assign some probabilities to U, C, and D. So this is what I'm going to do. I'm going to call U. I'm going to assume that player 1 plays U with probability Q1, C with probability Q2, and D with probability 1 minus Q1 minus Q2. All right? And then see what Q1 and Q2 values make player 2 indifferent between M and R. Why do I want to do that? Well, don't forget, I am looking at equilibrium where P is equal to 1/2. Meaning, player 2 is mixing, randomizing between M and R. Whenever a player randomizes, it means he is indifferent between these 2 actions. So, I have to find, therefore, probability values of Q1 and Q2 so that expected payoff of playing M and expected payoff of playing R are equal for player 2. This is what I should do. Clear? So one question leads to another. All right, so this is how I go. So the very first question I had was, is there any mixed strategy Nash equilibrium where player 1 plays D with some positive probability? And the answer to this is yes. If P is equal to 1/2, D can be played with a positive probability because it's a best response. But what I also noticed, when P is 1/2, not only D, but also U and C are also best response. So therefore, I summarized my case 1 as, well, if P is 1/2, then U, C, D, all the strategies of player 1 is going to give him exactly the same payoff. So he can randomize between all these 3 as he wishes. All right? Now, well, case 2 is, well, P doesn't have to be 1/2, obviously. We don't know. But if P is different than 1/2, you know what? In this case, D is not a best response. So it can never be part of Nash equilibrium. So this case is rather simpler because you can just eliminate D, all right, and just look at this 2x2 game and find the mixed strategy of that game. All right? It's very simple. So I'm not going to look at case 2. It's very straightforward. But I'm going to look at case 1. Because case 1 is more involved, detailed. So case 1 says the following. Well, P is 1/2. Good. Player 1 is playing something between U, C, and D according to some probabilities. Q1, Q2. 1 minus Q1 minus Q2. But the thing is, because P is equal to 1/2, it means, look, I am looking for a mixed strategy Nash equilibrium. So if a player is randomizing between two pure strategies, well, his expected payoff must be the same. So because P is equal to 1/2, or P is positive, all right, other than 0, well, that means player 2 is indifferent between M and R. Mathematically, what does that mean? His expected payoff of playing M must be equal to his expected payoff of playing R. So I have to solve this equality and see what I will learn about Q1, Q2, 1 minus Q1. As long as you learn something about Q1, Q2, it will tell you what to say about 1 minus Q1 minus Q2. So here, a comma, what is the strategy of the first player? Well, I'm going to denote, these are second player strategy, all right? The location shouldn't confuse you. If it does, sorry, let's put M here and then R here. So these are the first player strategy, and I call them Q1, Q2, because I don't know what they are yet. Maybe they're 0, possible. Maybe not 0, I don't know. We'll see about that. So expected payoff of player 2, if he plays M, what is it? He's going to get 4 with Q1 probability, 6 with Q2 probability, and 5 with remaining probability. So his expected payoff then is 4 times Q1, 6 times Q2, and 5 times 1 minus Q1 minus Q2. This must be equal to his expected payoff of playing R. 5 times Q1, 2 times Q2, and then 6 times remaining probability, 1 minus Q1 minus Q2. Okay? So if you solve this, well, let's simplify it. I have 5 here, minus Q1, because 5 is minus 5 plus 4, so minus Q1. And then minus 5 plus 6, so it's plus Q2. Equals, I have 6 here, 5Q1 minus 6Q1, so it's minus Q1. And then 2Q2 minus 6Q2, so it's minus 4Q2. Good. Minus Q1, both on both sides. So they cancel out, regardless of the value of Q1, right? So what do I have? I have 5 here, 6 here, send 5 to the other side. So what I'm going to get is, let me continue here. I have minus 4Q2, send it to the other side. I'm going to get 5Q2 equals 1, so Q2 must be 1 over 5. Okay, so what does that mean? Well, first off, Q1 is disappeared. What does that tell me? That usually confuses students when something disappears. It shouldn't actually.
It doesn't matter.
Very good, exactly. The value of Q1 doesn't matter. Whatever the value of Q1 is, this player is going to be indifferent between, the second player is going to be indifferent between M and R, as long as, if and only if, Q2 is exactly equal to 1 over 5. So the value of Q1 is irrelevant. Okay, so let's put Q2 value here, 1 over 5. What does that mean? That means as long as Q2 is 1 over 5, it really doesn't matter whether player 1 plays U with probability 0 or, probability positive. The remaining probability, 4 over 5, must be split between U and D, right? Because all the probabilities must add up to 1 eventually. But 1 over 5 must go to C, so that player 2 is indifferent. So how we split 4 over 5 between U and D is irrelevant. So basically that's it. I actually found millions of, infinitely many mixed strategy Nash equilibrium. That's it. That's the end of case 1 analysis. All I have to do is just sort of collect them together and then mathematically or logically state them correctly. So how can I do that? Remember, the mixed strategy Nash equilibrium are usually denoted by the probabilities of each player playing them. So let me just open up some space here. So player 1 is playing Q probability U, 1 over 5 probability C. I have to fix 1 over 5. Because if it is not, player 2 is not indifferent. For Nash equilibrium, this has to be 1 over 5. This must be 1 over 5. And then 1 minus Q probability, obviously, they have to add up to 1, be careful, D. So this is player 1's strategy. Player 2's strategy, 1/2 M, 1/2 R. So this is a strategy, a mixed strategy Nash equilibrium. Nash equilibrium in mixed strategies. Okay? But there's only one more thing that you should be careful. Q, can it be any number between 0 and 1? No. Don't forget, Q plus 1 over 5 plus 1 minus Q must add up to 1. All right? Q plus 1 over 5 plus 1 minus Q must add up to 1. So here, therefore, if you choose, if you choose Q, you have to be careful. How can I modify this strategy? There's got to be some modification here. Yes? Okay, good. What he's suggesting is, instead of writing 1 minus Q, let's write 4 over 5 minus Q. Because if we do, instead of 1, 4 over 5 minus Q, well, regardless of the value of Q, all right, this always will add up to 1. But then, yes, Q can't be between 0 and 1, because if Q is, for example, higher than 4 over 5, this is going to be some negative number, but the probability can't be negative. So therefore, Q must be coming from 0, closed interval, and 4 over 5, at most 4 over 5. So now it's complete. The picture is complete. So this is the set of all mixed strategy Nash equilibrium, all right, when, in case 1, when player 2 plays M and R with equal probabilities. End of case 1. Case 2, as I said, what if P is not equal 1/2? In this case, as I said, I'm just repeating myself, I know, but you're going to ignore D because it will never be a best response. So the mixed strategy has to be in this 2x2 game. Just calculate it. And in fact, if you do that, it's going to be one of those guys, I guess. I'm not sure though. So that's it.